So our point of collision is going to be the movement direction impact point. We've got the normal to the collision, which is going to be the movement sweep collision normal. So now we need the perpendicular to the normal of collision. So we need to rotate a vector so this, we were moving to the right. This is going to be the normal. So for us, we want to rotate this way. But if we were going this way, we're going to want to rotate it that way. So we're going to want to rotate this vector based on our direction. So where is that? Rotate vector by velocity. I believe that's correct. We'll double check our math when we get to all the things. So that's going to be the perpendicular to the normal of collision. So we've got our impact point. Do we actually want that impact point? I thought we were. It's going to be our height times the perpendicular to normal collision. All right. So is rotating a vector by the velocity. Yeah, so these should already be normalized. So we've calculated our height, our point of collision. Are we going to be adding to the point of collision, or are we going to be adding to... I thought what we wanted to do is take this corner and then move it up to, like, you know, right above the object. So we move it up based on the height. So we need our bottom right or our bottom left point. So we actually need to get our we need to actually calculate our bounding box is what it looks like. Like we want a calculate bounds function. So we need an f box, and we got like box dot something rather. Let's see. We got our min and max vectors, so we're going to do like set our min equals f vector 0 vector. So we're just going to return the box if we don't have any components otherwise. For every one of these, we need to get our bounds. So we're going to do like if box.min.x is less than box.min.x, then box, well, I'm going to call this one iter box. Box.min.x equals iter box.min.x. On IntelliSense, I don't need your help with that. This is how copy-paste errors happen. And you can see it in real time. There's probably an easier way to do this with some cached functions that they've already written somewhere, but I don't know about them, so they don't exist to me. But from my point of view, the physics are evil. Alright, so this will calculate our bounds. So basically we want our f-box bounds, and we're going to calculate our bounds. And based on our left or right, we're going to basically take our min coordinate or our max coordinate. So if, let's see, what is it, if our velocity.y is greater than 0, f vector, let's call it the corner. So if our corner is greater, then we're going to want our maximum coordinate, seems like. So we'll take our maximum, which should be, actually no, we should take our maximum y and our minimum z. So corner.x is always going to be 0, because we're not moving into the background with these guys. They're all running in a plane. And we want to take our maximum y and our minimum z. So corner.z equals bounds.min.z, and corner.y equals bounds.max.y. And for this one, we're going to take our minimum y and our minimum z. So minimum z is always our corner, and it's going to be either maximum or minimum y. Not too complicated. So our step 1 vector is actually going to be, that's going to be our vector, and we're going to we're basically doing this so we can get the raycasts. Is this correct? Is this correct? Anyway, do we have all of our information? See you later, issue. The good having you around. So have a good one. Oh man, there's Adam actually making some shirts. Very nice. Those look pretty cool. So, excellent. So, if we're going to mantle, what are we going to do? We are going to want to sweep in the direction perpendicular to the normal of collision by our height. And then we're going to try to sweep to the right. So, the sweep position. So F vector, so step 1 sweep position is going to be our current position. What is our current position? It's going to be a new position. Step 1 sweep direction. So step 1 sweep direction is going to be our step 1 vector. So we just have our step 1 vector here. Well, this is our step 1 vector. This is our step 1, yeah, right. Step 1 vector is not step 1 direction. Step 1 direction is perpendicular to normal of collision. The distance, so it's going to be step 1 sweep distance is going to equal our height. Basically, this is going to be like for int 32, I equals 0, I is less than max mantle attempt iterations. It's going to be our height times I, and I is going to start with 1 and do less than or equal to. So that's going to be our sweep distance. So we sweep to location 1. If we hit something, that's a good question. So if we hit something with our sweep up to this location, we didn't actually cover this case, did we? So this is the case where we're like, what is this case? If we hit something when we do a sweep. So we've run into something, and this object right here is going to sweep up by its own height. So it's going to sweep up by its height. So it's going to like go from here to, I mean, yeah, so it's going to be up to here. Well, that's because we're not sweeping up by our height, are we? We're sweeping up by not actually the height. Ah, man. I thought we solved this. Where is... Back to thinking about collision. Shit. Alright, so it's not necessarily our height, is it? Like, we're sweeping so that like our bottom right would be here. That's not exactly right. We're just trying to find the normal, aren't we? To start with, and that's going to give us the height that we need to sweep. So we actually want to do our ray cast. So okay. We're not doing our sweep first. We're figuring out our frickin' normal first. So we're going to do a ray cast, or do we need to do a ray cast at all? It looks like the only ray cast that we need to do is going to be the ray cast towards the thing. So we're going to want our step 2 start. So F vector. Ooh, we're going to need to do ray casts along each one of these just to make sure that there's no collision, aren't we? Because it's basically like we take this, we take our box, we take this guy, and we're gonna take it up here, and we're gonna take it to the right, and we're gonna take it down. But we're gonna do it plenty of times. Like we're gonna take it up, 2 times, and then we're gonna take it over, and then we're gonna take it down over here. So we actually do need to cast the ray from this location. So it's going to be F vector step 1 start, and that the step 1 start vector is always going to be our corner. So, and the F vector step 1 direction is going to be perpendicular to the normal, and the float, the step 1 ray distance is going to be equal to our height times I. And we need to cast that ray. And then we need to cast, so cast the step 1 ray. If it hits, what do we do? So if our ray actually hits something, so we went like this, we grabbed our location, and we cast it up by our height, and we hit something, then there's nothing for us to do. Like, then an object has to be like right above us, and we're done. So if it hits, then we break out of the loop. Like we're done simulating our movement. Alright, then we need to do F vector step 2 start, and that's going to be step 1 start plus step 1 ray distance times step 1 direction. And F vector, the step 2 direction, is going to be our normal. So the normal to the collision. It's actually going to be the inverse of the normal. And float, step 2 distance is going to be our small value. So tiny float over in that direction. So nudge it a little bit. And we need to do a ray cast there. So cast the step 2 ray. If it hits, we break out of our loop. So does it matter if the ray hits? I don't think so, actually. I don't think we actually have to cast the step 2 ray. We just have to cast, so F vector, because the step 2 ray might go a little bit higher and it might hit something. It might mathematically just perfectly hit like the ceiling or something. That's not a problem. So this is going to be step 3 start is going to equal the step 2 start plus step 2 distance times step 2 direction. And the F vector step 3 direction is going to be the inverse of the perpendicular to normal of collision. And the float step 3 distance is going to be far enough. We're going to want to cast that. And we want also the F vector step 3 inverse direction. and that's going to be perpendicular to normal because we need to do a cast in both up and down. No, that's not true. We are going to want to we're trying to rule out a sweep by casting the ray in both directions and getting the... Yeah, that doesn't make sense because that diagonal angle isn't going to work. So we're just going to cast the ray, and then we're going to get the normal to the surface. And then once we have the normal to the surface, we can cast a ray straight up or whatever. We can actually just do our sweep tests, and that should tell us if it works. So we need to cast our step 3 ray. We need to grab the normal of the surface as well as the point of impact. So we're going to get F vector point of impact. Let's call it something specific. Let's call it step 3 impact location. Let's call it F vector step 3 impact normal. Okay, and what we need to do then, so we've got the normal, we've got the thing, we need to, so we've got this location right here. So we want the Z location, so we want like our on our F vector, we want our sweep. We want to figure out, alright, so we have the location. We want to know how far we need to sweep the actual object up to get to where we're going. So what needs to happen is this is going to be our sweep end is what we're going for. This is going to be sweep 1 end location. I guess it's sweep 1 like sweeping, we're going to be sweeping by the perpendicular to the normal. So we're basically, we're needing to move this direction, and we know our y coordinate here, so what we're doing is we're taking our we want the magnitude of the sweep in the sweep direction, and that's going to be like we're going to take, because we know the y right here, it's going to be the difference in the y coordinate, the z coordinate projected onto the perpendicular to the normal, and then we take the magnitude of that vector. So if you can see that little triangle right there, we need to do that whole thing of like a squared, b squared, c squared bullshit. So we need to get the difference in, so we're going to do the height difference is going to be, because there's no way in hell this is different, like the height difference is negative, so we're going to take our step 3 impact location dot z, and we're going to subtract our bounds dot min dot z from that, and that's going to give us our height difference. And now we need to take this we need to, yeah. Do we have vector projection math library stuff? Alright, so it looks like f vector has a project onto sort of thing. So what we're going to want to do is get the vector. The f vector should be like our projection vector. Like, should we actually project, like, so if we're here and we just got this point right here, and our object is like tiny, and we're gonna mantle all the way up there. If we took this vector here and we projected it onto this direction, it's going to move us right here, and then we can sweep. Supposedly we could sweep up, and it looks like we might hit the lip on this, so we actually have to move a little bit farther. So we have to like project the vector and then add a little bit to it so we can kind of nudge over the top. Is that correct? So we project this vector. Yeah, I think so. So the projection vector is going to be the bounds. It's going to be our corner. It's going to be our step 3 impact location minus our corner. And what we're going to do is we are going to call project. And we're going to project onto. And we're going to project it onto the perpendicular to normal of collision. So this is going to be f vector sweep direction, or sweep vector. And what we're worried about is the float. The sweep 1 distance is going to be the sweep vector dot magnitude, or size, and we're going to add to that size this small tiny float. So we're going to nudge up. Why is this complaining? F vector has no member project onto. Oh, it's project onto, like that. So that's going to be the sweep vector size times the tiny float. We need to sweep the object by the sweep 1 distance in the sweep vector direction. Let's just do a sweep vector dot normalize. And if we collide, then we break out. Then we're finished. We were unable to do anything. So then after we have swept up, we've got our box right here. We need to then do a sweep in the inverse of the normal, and we're going to need to get the distance for that sweep. So we're going to do the f vector and that's going to be sweep to direction is going to be the inverse of the normal. Movement, sweep, collision, normal. And the sweep distance, we're going to need to, like, we got the projection of that vector, we're going to need to subtract, yeah, we're going to actually do f vector sweep one direction equals the projection vector. Well, sweep one direction is going to be in the perpendicular to the normal. So this should go, yeah, sweep vector. Do we need this vector? This is the projection. So we should, this is, we're going to need, yeah, so this is the projection vector is what I should call this. So this is the to project vector. So we're projecting it over there, and the projection vector size, yeah, so sweep one distance is the size of that plus a little bit more. And for our sweep to direction, it's going to be a normal to the collision and the float. We actually need another vector here, which is the f vector. This is going to be sweep to, let's just call it distance vector. And that's going to equal the step 3 impact location minus the projection vector no, it's going to be step 3 impact location minus the projection vector plus the corner. And that's basically like we take our corner, we add our projected vector, and we get this point, and then we basically, yeah, we need to actually subtract. We need to do step 3 impact location minus this vector, and that'll give us that direction and that magnitude. So how far should we be sweeping is going to be, yeah, so this is going to be sweep to distance is going to be the size of that vector. And again, I think we're going to have like add a little tiny float to it just to make sure we're kind of nudged over into that direction properly. So sweep the object by the sweep to distance in the sweep to direction. If we collide, then we continue in this loop. So that should put us right on the edge of this thing. And then we sweep down and settle ourselves. Is that what we do? So the other, so that puts us on the direction there. But there was the other thing we were talking about, which was if we did this, and instead of sweeping to here basically, and then moving right up here and settling, saying maybe we move to like, we move to here, which is a little bit higher, and then we just move by the normal onto this thing. And the question would be, so if we had this point, we know our corner should be there, so we'd basically just be like, well, how far does our corner have to be to, we would just set our y coordinate of the corner to that, and then, well, let's see. We've got this point, we've got our corner, and we want to project onto, not onto the vector, which would do this. We want to project onto here. And we move it all the way over here. And then we move it over. Which seems wrong. We don't really want to move it over. I think what we got is correct, where we're moving it to here. And then we're moving it up, over, and then down. We're going to settle it. And then we can just continue moving on the normal of the surface. So I think that's what we want. So sweep 2 has been completed. Now what we want to do is we want to settle our object. So we want to set ourselves, our F vector settle position is going to be the so we swept from 1 to 2, or we swept from the original, so it's going to be, this is going to be sweep 2 distance. Yeah, shit, we need to get the sweep 2 position. So we need the F vector here, we need sweep 1 position, and that's going to be our current position. Do we have that just set up here? Is that just new position? Yeah, so our sweep 1 position is new position, our sweep 2 position is going to be new position plus sweep 1 distance times perpendicular to normal of collision. That's our sweep 2 position, and our F vector settle location, settle start should equal our new position plus sweep 1 distance times the perpendicular to the normal plus our sweep 2 distance times our sweep 2 direction. And we have the tiny floats on there already, so we then basically do a we need a time quanta for how long it actually took to mantle on this object. And I think we're just going to say that mantling takes 0 time. Is that true? Should mantling take no time at all? Because we're not really going to have, this is not for, climbing up a cliff. Climbing up a cliff is just actual motion. This is for just a subframe getting over those little stupid bits and bobs. So I think it should take no time at all. So we should do our settle start with our floor stick distance. floor stick distance should be our sub delta t times our floor stick distance stuff. So we snap to the floor, and then we return delta t. Sub delta t, sorry. Okay, well that makes sense. Kind of makes sense. Step 1 ray distance is going to be the same. Step 2 ray distance is good. So what is this going to do? It's going to pop us on top of stuff. So if we're walking up steps, we're going to go up steps properly. We're going to just pop right on top of them. We're not going to lose any speed. Is there any reason to do anything else about this? Like, should we put in submantling time in terms of you could kind of partially mantle up on something as you're going? So you are going around, there's a step, you run into the step, and it's basically like, okay, sure, you totally could get on top of this step, but you only got like a tenth of a second left in your frame. So we're going to take you, and then we're going to move you by the quanta that we need. And how much does that actually, how much does that move take? Because we're already hitting this thing, moving in our direction. But we get into problems where you're not on the floor anymore, so we'd have subframe issues with movement. Well, we can solve subframe movement stuff later if we just do 0 for this. Like, Brackenwood doesn't have stairs. And even if it does have stairs, we can always have the collision geometry of the actual object be a ramp instead of staircase, which is fine. That's not a problem. That's pretty much what most people do anyway. So really we're just like getting over stupid little pieces of crap on the ground that should not block us. And we're just continuing our motion properly. So I think we're good. So let's do this second chunk here. We move to the point of collision and settle, which we have, yeah, let's just move to the point of collision and settle. Then we need to continue moving perpendicular to the normal for the extra delta t. So moving perpendicular to the normal is a sweep test. So we're going to do f vector start position is going to equal get position. Yeah, you got a point there, but the physics movement is separate from the actual animation in a lot of ways. So because we're trying to get the motion proper, and like if we go into like actual stair step mode and stuff like that, then usually like you're actually on stairs and you have special logic for your person, like traversing up and down steps and all sorts of crap. So I don't think we're doing that at all. And then like in 3D world, usually you got like a capsule for your character, and then you've got like this IK crap for the legs, and the legs kind of up the stairs. So the legs are like totally fake. They're not like real collision, at least for the movement of the character. And you kind of just like settle the capsule onto the ramp of the stairs, and then you have like a separate collision layer for the actual stair thing. And yeah, the stairs are like, let me see if I can find a good example of like kind of what you're talking about. Um, Can I with these stairs? I think if we watch this guy come up, I think he does. He has to actually get onto the stairs and then do like this stair animation thing there. I think that's kind of what like they actually have him lock into a specific set of animation on a very specific piece of collision geometry. Like he can't jump on it, he can't do any of the other crap. He has to get perfectly on the stairs to be able to walk up it. And that's kind of how like 2D stairs usually work if they're specific. So we're not going to do that sort of thing. I think we're going to do more like the sliding thing because stairs aren't like a huge part of our game. And if they become a large part of the game, like if it's Bitey in modern day and he needs to go up and down an escalator or something, well, we can handle that with a different set of motion. We'll have like a if you're on escalator collision block and do it that way. Anyway, so the start position is our current position, and the direction of motion is going to be, we're going to have to recalculate this. It's going to be the surface normal times the velocity y. So we're going to need to get the surface normal, aren't we? Bitey's Adventures of the Mall, I would play that game, and Bitey would have to have like a whole dress up simulation part. He'd need to put on some hats and like maybe some pants and then some dresses or something. That would be a pretty sweet game, to be honest. Because Bitey has no idea like that only girls wear dresses. And what gender is Bitey anyway? All right, so we need to rotate our surface normal. Our surface normal is going to be the normal to the movement direction impact point. It's going to be perpendicular. It's going to be the movement sweep collision normal. That's going to be it. So it's going to be, we're going to grab the movement sweep collision normal, and we're going to rotate the vector by our velocity. Add the minigame. We'll see what we can do. The cool thing is, since we got like WebKit windows for the UI, we could code the like if we were gonna make like a mini game or some like stupid little bullshit and throw it in there, we could totally just do that in JavaScript and HTML and just throw it on there, right? Not even a problem. Hell, we could host a web page with like simple mini games and just view it in the game, and you can go play. So we have possibilities for easy things. That doesn't mean we're going to do them. It just means we have possibilities. All right, so we're going to rotate the direction vector in there, and we need to know the distance that we're actually going to move. So we're again, hit distance is physics far enough, sweep component, movement distance. Movement distance is going to be the absolute value of the y times the delta t. In this case, it's not delta t, it's sub delta t. sub delta t is not correct. Sub delta t is how far we actually already went, isn't it? Where the hell is sub delta t? Sub delta t is how far we have already simulated. Extra delta t is how far we have yet to go. So actually we need to change this to extra delta t returning here, and this needs to be extra delta t, and we need to yeah, it could work. What we're going to do here for the sweep is we're going to move by our time, and no, oh my god, this is not extra delta t. We're returning the time that we've successfully simulated, and the time that we have successfully simulated is only sub delta t. Okay. Ugh. So sub delta t is good. That's what we want there. Right here, we're trying to move by extra delta t, and we are going to see how far we are able to move. So sweep in the movement direction. So only just do bool collision. Actually, no, let's do f vector. If there is a collision, move to the point of collision. Calculate the amount of time that has passed, add that to sub delta t, and return. If there is no collision, move to the sweep location and return delta t. Okay, so we've pseudo-coded out the whole thing, so we just have to actually write it. And it only took us 5 hours to get to this location. Anyway, I'm going to take a very quick break, and I'll be back. Man, it's starting to get colder in here. I guess that's because it's 1:30 in the morning over where I am. Yeah, and if anybody wants to support my friend Ivan, who's and buy the shirt I'm currently wearing, you can always check him out on Amazon and order it from there. He's another indie dev, um, also a good friend. So whatever works. All right. So where the hell were we? We pseudocoded out all the things, and basically we need to actually code out the sweeps, the creeps, the bleeps, and the sweeps, and all that. So why don't we get started doing that, huh? And the thing is, after this is done, we should be able to run around our world. We can't jump over everything, but we should be like instantly clear obstacles, and we'll any little seams in the ground we should just nicely do. Stairs we're gonna kind of stick on top of, because we're not actually gonna have stairs in the game. We're gonna have ramps, stuff like that. So when you see stairs, there will actually be a ramp. At least I think that's what we're gonna do, because there aren't really gonna be any real stairs in the game. And if we do actually need stairs, we'll have to throw in a little bit more stuff here. Like we'll need some We'll basically have to split up like kind of the mantling stuff into something that can take a certain amount of time, and then like when you're climbing up a stair on a frame, it'll like figure it out and be like, oh, well, you're currently actually stepping up something, so we shouldn't settle you on the ground yet until you're finished with, the mantling thing, that sort of stuff.